Hi, I am Sanjay Patel. In this video, I am going to prove a sufficient condition for a ring to be a field. We know that what is a field? A field is a commutative ring with unity in which every non-zero element has multiplicative inverse. We have also proved in our earlier videos that if f is a field, if f is a field, then f has no proper ideal. Then f has no proper ideals. What I want to prove is the converse of this result in this lecture. If f is a field, then it is necessary that it must have no proper ideals. You know what is an ideal and what are proper ideals. The ideals I equal to singleton 0 and I is equal to the whole ring in any given ring R plus dot. These are known as proper ideals. These are known as these are known as improper ideals. These are known as improper ideals. And here we know if f is a field, then it has no proper ideals. Means only ideals, that is only ideals in the field are singleton 0 and I is equal to R. No proper ideal means there are only two ideals in this field. Remember, every ring has always these two ideals, singleton 0 and the whole ring itself. And these two particular ideals are called improper ideals. Okay. So let us prove the converse of this statement as a result, which is another important result about field. Let me write this way. If a commutative ring R, plus, dot with unity has no proper ideals, then prove that R is a field. So this is actually a converse of the above result. F is a field implies f has no proper ideals. If a ring with unity and commutativity, it has no proper ideals, then it must be a field. Okay, let us prove this. So I start with an arbitrary commutative ring with unity. Let R plus dot be a commutative ring with unity, and suppose R has no proper ideals. So this is given to us, and we want to prove that R is a field. Okay, we know what is a field. A field is a commutative ring with unity in which every non-zero element has multiplicative inverse. We are already given that this R is commutative and it has unity element. So what remains to prove is only that the every non-zero element in R has multiplicative inverse. So since R is commutative ring with unity, say let us write a symbol 1, it remains to prove it remains to prove that every non-zero element, remember, every non-zero element of R, every non-zero element of R has multiplicative inverse, as multiplicative inverse. So to prove this, we must start with any non-zero element in the given ring. So let us consider, let A belongs to R and A is not equal to 0. What I should prove is it has a multiplicative inverse. Since A is arbitrary, it follows that every non-zero element of R has multiplicative inverse. Now what is a multiplicative inverse? Given a non-zero element A, if you can find another element B in the ring such that A into B is equal to 1 and B into A is equal to 1, then B is called multiplicative inverse of A. So our aim is to find such an element B. Okay, we are given this A and it is not 0 in the ring. Using this element A, I define the ideal generated by the element A, rather the principal ideal, as you know. So let us define an ideal define the set I. You know this symbol, it is called principal ideal. So define a set I is equal to set of all elements of the form R into A, where R belongs to capital R. Okay, we know that this I is the smallest ideal in a ring, in the ring R, containing the element A. So we know three things about this set. It is an ideal, it is the smallest ideal which contains the element A. It means A belongs to A, is there. First of all, note that as A is not equal to 0, the set I is not equal to singleton 0. It contains at least one non-zero element, because unity is also there. So I contains 0 as well as one more element at least. Okay, because the ring R has unity. Fine. So note that A is not equal to 0 implies A is not equal to singleton 0. Okay. We have already proved, or we had already proved that this set I is an ideal. Okay, is an ideal of the ring R. And what is given in the hypothesis in this theorem is that the ring R has no proper ideals. So let us use this fact that R has no proper ideals. Okay, so since I is an ideal and R has no proper ideals, so only possibility for I is either it is singleton 0 or is equal to the whole R. So now R has no proper ideals. R has no proper ideals. That is given to us. Okay. Therefore, this I, which is an ideal in the ring, is either it is equal to 0 or I is equal to the whole ring R. Okay. But we have noted here that I is not equal to 0. So therefore, I can write I is equal to R only, because of our this remark that A is not equal to 0 implies I is not equal to singleton 0. So I is a non-zero ideal here. So this is not true. So I is equal to R only. Now the important step, we have the ring R as unity. So now we know that 1 belongs to R. That is also given in the hypothesis that R is a commutative ring with unity. So 1 belongs to R, and that implies 1 belongs to the set I also, because I and R are equal. Okay. Now if 1 belongs to I, you know what is I? I is this set. I is this set which contains elements of the form something into A, where something belongs to R. So every element of I can be expressed as some element of the ring into the fixed element small a. Okay. So I can write, therefore there exists some element in the ring, say let us call it R0, belongs to R, such that I can write 1 as R0 into A. I can write 1 as R0 into A by definition of the ideal I. Okay. Now R is a commutative ring. So if 1 is equal to R0 into A, then we can also write A into R0 is equal to 1. So this implies we have say R0 into A is equal to 1 and is equal to A into R0 because R is commutative. So we are using all the conditions given in the hypothesis: commutativity, unity, and it has no proper ideals. All the three things are already used. So R0 into A is equal to 1 and is equal to A into R0. What is the meaning of this statement? We know whenever this thing happens, we say that this A is an inverse of R0 or R0 is an inverse of A. They are inverse of each other, multiplicative inverse of each other. So I can write this implies R0 is the multiplicative inverse of the element A, and we know that R0 belongs to capital R. Hence our aim is proved. What was our aim is we wanted to show that every non-zero element A has multiplicative inverse, and we have found that R0 is the multiplicative inverse of A. So thus every non-zero element in R has multiplicative inverse in R. So therefore R plus dot this ring is a field, because we are already given that it is a commutative ring with unity, and we have proved this fact, so it is a field. So the converse of that theorem, what we have proved in our earlier video, that if F is a field, a ring is a field, then say it has no proper ideals. Conversely, if a commutative ring R with unity has no proper ideals, then it must be a field. So I can combine these two facts and write another statement as a theorem, which is combining both the results, this theorem and the previous theorem of the earlier video. So I can write, let R plus dot be a commutative ring with unity. Then R is a field if and only if R has no proper ideals. R has no proper ideals. So just this theorem and that previous theorem, combining the two theorems, we can get this necessary and sufficient condition for a ring R to be a field. Okay, so this is all about this today's lecture, and we'll be going to study some special type of ring in our next lecture, which is again an important type of ring for the higher studies of ring theory. So till then, goodbye. Thank you.